Well, hello again. This is the last of the operation fractions. We're doing division today. Probably talk about this a little bit, but some people are not excited about doing division of fractions, and the argument that they make is that those situations never really show up in the real world. But we're going to do a little bit just so you can see how you can make sense of it. We'll see that we're actually doing an estimation in the end, but that's okay. We'll model it anyway. We'll also have it the second problem here will involve using a unit that's not a unit fraction to measure with, and so it'll be a little bit harder. That's something you might want to consider yourself, whether or not you want to go that far with division of fractions where your divisor is not a unit fraction. It just adds a little bit of complexity, and you'll see when we get there. We're going to do measurement division only. The reason that I think that's one that we should focus on is that sharing division, to find a context that even comes close to that, is so contrived. And you think about sharing in any way, like if you had 3/4 of a pound of chocolate and you want to share with 2/3 of a person. If both the numbers are fractions, sharing division doesn't make an awful lot of sense. It will make sense if you have some whole numbers involved, but with the ones we're going to model here, with where both the numbers are fractions, because that's where the modeling is really helpful to figure out what's going on, we're only going to do measurement. And measurement is just like with whole numbers. If you have 15 objects and you want to make groups of 3, you're going to measure with groups of 3, 3, 3, 3, 3, and just see how many groups of 3 it takes to make out of 15. We're going to do the same thing with fractions. You've got some portion of a whole that you're starting with, and you're measuring with a smaller piece, like a third of wonder how many half cups it takes to make 2/3 of a cup. So you're going to measure a half a cup, see how many of those it takes till you fill up to 2/3 of a cup. And it will involve how much of that last half cup does it take. So you'll see in the context here that if you put it in a measurement context, we can make a little bit more sense of it, although in the end it involves an estimation in the real world anyway. So a lot of initial topics here to talk about before we actually start modeling. We're going to do two fractions. As I mentioned, if you had a whole number involved, something like starting with 5 wholes and you know how many thirds there are, that's something that kids should deal with and you should have dealt with before you're starting to do with these contexts that have two fractions with them. So whole number divided by fraction, that's something that you should make sense of as a prerequisite skill. That should be fairly easy to deal with, since kids can easily see that each whole has 3/3 in it. So if you had 5 wholes, you've got 3 times as many thirds as there are wholes. If there are 5 wholes, there's going to be 15 thirds, something like that. I already talked about measurement, that it's kind of a silly or contrived situation if you try to do sharing. Some educators, as I mentioned, have argued that they don't even really want to do division of fractions. In fact, some curricula have left division of fractions out entirely, but they actually did it on purpose because they argued that it's really not a real context and you never solve a problem like that in the real world, really. They tend to be very contrived. But I think it's worth seeing it because we can actually see what the operation of division of fractions looks like at a material level. So we're going to do something. We're going to choose a context, and it's the only context that I know that kind of makes sense. It's probably happened to all of us. And so it may be the only one worth considering, although if you can find others. Be careful with the idea if you say it takes 3/4 you suppose you had 3/4 of a yard of ribbon, and it takes a third of a yard of ribbon, a yard to make a bow. How many bows does it take? Well, that's actually asking how many thirds does it take to get up to 3/4. But recognize that last third that you use doesn't make a whole. It's not long enough to make a whole bow anyway. And so your answer is really a whole number answer where you just kind of truncate and leave off the end. So be very careful about context for division of fractions to make sure you're doing something that really makes sense. It's like the old thing about, if you can get 40 people on a bus, but you have 130 kids that you need to put on a bus, how many buses does it take? And you don't want to end up saying something like, well, it's 3 1/4 buses. because how do you do a fourth of a bus? I mean, it takes 4 buses, even though you didn't get all the way up to whatever it was, 160 was what it would really hold. So be careful with the context with division of fractions. So here's the cooking context. I think it's happened to lots of people. The recipe calls for 3/4 of a cup of sugar, but you get ready to make it, and all you can find is that 1/3 measuring cup. And you don't want to wash another cup. It's the only one you can find. And so, I don't know, maybe men are worse at this than women, but they just say, I'm just going to use the 1/3 cup. It's what I've got. You know, I'm going to guess anyway, and so I can get pretty close, I think. And that's why, just like with the other operations, estimation is really, really important. You ought to be able to look at this context and think about, if I can only find this 1/3 cup, how many times am I going to fill it up and pour it in? Well, I need to get up to 3/4. I don't want to fill up the 1/3 cup 3 times because that would give me a whole cup. And 2 is not enough, so I know it's somewhere between 2 and 3. And you might end up arguing, you know, that it's, you know, that if I do it twice, it's only a little bit short of 3/4 because 2/3 is just a little bit away from 3/4, and so I'm going to just put a little bit more in the last time and pour it in. So an estimation is really important, at least to check at the end to make sure that you've got an answer in the real world that matches what your estimation was like. We talked about this before. Even if you had figured out that it was exactly 2 1/4 of 1/3 cups, which means you would fill the 1/3 cup up twice and then 1/4 of the way full the last time, since there really are no 4th marks on that 1/3 cup, at least generally you don't have 4th cups that, or the 1/3 cups that have 4th marks on them, you're going to estimate anyway, and it's not an easy estimation, especially if the cup is shaped like that. So in the end, this context really requires estimation, even if you knew the exact answer, which is one of the reasons why some people say, you don't really need you know, exact answers to division of fractions questions, and that's why some of them leave it out of the curriculum. But I think you'll like this context, and even if you're stuck with estimation in the real world, when you try to apply your answers to the real world, I think it's worth doing. So here's the problem again. The recipe needs 3/4 of a cup. All you can find is a 1/3 cup. How many 1/3 cups could you use? In other words, how many times do you fill it all the way up, and then how much the last time, because that's the only cup you've got to measure with. Notice that this context, since we're talking about cups of sugar, really does imply of a whole cup. So it's 3/4 of a whole cup of sugar that the recipe calls for. The measuring cup that you have is 1/3 of a whole cup. It's not 1/3 of what you have. That would be a silly cup to say whatever I fill up here is 1/3 of all the milk I have in the refrigerator. You would never do that. So it's all about whole cups. And division is unique compared to all the other ones in that in the end your answer is about a different unit. It's asking you how many 1/3 cups, and so the 1/3 cup, that smaller piece, is now your unit because that's all you have to measure with. You want to know how many of those. All the other operations ask in the end, how much of a whole cup does the person have if you add these together? How much of a whole cup is left if I take something away from the part that I started with? How much of a whole cup does somebody give if I give them 1/3 of the 2/5 cup that I had to start with? You want to know how much that is? It's always answered in terms of whole cups. But with division, the unit has changed. The new unit is 1/3 cups. So just like before, we're going to make a wall with Cuisenaire rods. We're going to try to act it out using this linear approach with Cuisenaire rods. Be similar to what you would do with a number line if you wanted to expand how you start the concept with Cuisenaire rods up to a number line model. That should work. And then we're going to measure and figure out how many 1/3 cups it takes and how much of that last 1/3 cup should I use. How full do I fill it the last time through? So we'll start by making the wall, and we have 1/3 and 4ths here. So we need a unit that's got both 1/3 and 4ths. And so we end up with a unit like this, and that's fairly close to what we have on the PowerPoint. But what I'm going to do, since I have this other rod here that actually is going to be able to represent the 12 rod, rather than having to make it with a 10 and a 2, I'd like it better when you can actually see that as a whole unit. So I'm just going to replace that so that you can see this is all one rod right here. That is the whole. And there's the 1/3s, there's the 4ths. Again, 4ths because it takes 4 of those to make up the whole. And you can see that 12 little rods going all the way across. So we made the wall. It's got 1/3s and 4ths in it. Then we act it out. So all you do I think this is so concrete that once you've made the wall and you make sense of what each fraction stands for, you just have to do what the problem said. The problem says that the recipe calls for 3/4 of a cup of sugar. Well, we know what the fourths are, and so this tells me that's how much sugar I want. But I only found this cup to measure with. So I'm just going to measure with it and see how many times do I use it. So fill it up once, I get up that far. Fill it up again and pour it in, I get that far. And obviously I need a little bit more of the last one. So you put another 1/3 cup down there, and you know it's going to take some piece of that. Well, you just measure to see how much of that it's going to take. So you measure that last 1/3 cup, and some people will either drop one of these down just a little bit, or they'll point to it and write or something. But notice this is 1 out of the 4 pieces it would take to fill the last 1/3 cup up. So this is 2 whole 1/3 cups and 1/4 of another one. So altogether, the answer to this division ought to be 2 1/4 1/3 cups. And in reality, that just tells you you fill one all the way up twice, and you fill it 1/4 full the last time. So we measured that, and now we're ready for the area model. So let me get this off. Okay, so area model here, again, we're going to draw the unit. We're going to subdivide it because we need to know what fourths and thirds look like. And we're going to count how many 1/3 cups it takes and how much of the last 1/3 cup. So let's draw the unit. This is what a whole cup of sugar looks like. And the recipe calls for 3/4 of a cup, so I need to know what that looks like, so I'm going to divide it into fourths. And I do not want any sugar out here. I only want to fill sugar up to this much, because I only want 3/4 of a cup of sugar. And it says all I can find is a 1/3 cup measure. Well, I need to know what a 1/3 cup looks like. So I'm going to subdivide the cup into thirds, into 3 equal pieces, noticing I don't have any sugar out there. I don't want sugar out there. But I do see that a 1/3 cup here is 1, 2, 3, 4 pieces. So if I fill up a 1/3 cup and pour it in, it's going to fill up 4 pieces. So I'm just going to, you can either do that with shading, say here's the first 1/3 cup. I like to also, though, just label it as there's the first one. I've poured in 1, there's the first 1/3 cup. But I can do it again, you know, and a different shading is sometimes helpful, different color, or shade it differently or something. But when I pour a 1/3 cup in, it uses 4 pieces. But I also like doing, here's the second one. So I poured the 1/3 cup in 2 times. Now, if I pour it in again, all the way up, it's going to fill up 4 pieces. I don't want all 4 pieces. I only want one of those 4 pieces filled up. So what really is happening here is that, and this is really helpful to point to this and say exactly what's going on. That little piece there is 1/4 of another 1/3 cup. See that? That's 1/4 of another 1/3 cup, because it's one of the 4 pieces it'd take. If I filled it all the way up the 3rd time, it would do 4 pieces there, but I only want one of those. So really what we're getting here as an answer is 2 1/4 1/3 cups. Notice the unit has changed. That's why I'm putting this 1/3 cups in. Here's the unit, because that's what the problem wanted to know, is how many 1/3 cups does it take. So we drew the unit. We subdivided to see fourths. We showed thirds, so we know what it looks like when I pour a 1/3 in. And then we shaded and counted. That little X there on the PowerPoint shows that 1/4 of another 1/3 cup that, that we're using. So what about a paper and pencil algorithm? So let me move this up slightly. So here was the problem. The problem says we've got 3/4 of a cup, and I'm going to divide it by 1/3 because I want to know how many third cups it takes to make 3/4. Now the order here is really important. If kids have trouble with this, you could give them a word problem that has whole numbers in it. It just says, if I've got, for example, let me see if I can write this up here. If I wanted to do 12, well, if I gave you the problem that says I've got 12 cookies, I want to put them in stacks of 3, how many groups of 3 can I make? Clearly, kids are going to say, that's 12 divided by 3. So you do the same thing here. I've got, instead of 12 cookies, I got 3/4 of a cup of sugar that I need. I'm going to make groups of 1/3. I want to know how many groups of 1/3 it'll take. That way I clearly see the order. It has to go in this order because this is the divisor here, how many thirds I'm making. Well, what really happened to this? Well, the 3/4 actually became, if you look back in the area model, actually became 9/12. That's an equivalent fraction. So it really became 9/12. And we're dividing by the 1/3, but what did 1/3 become? Well, when we did those subdivisions there, 1/3 is 4 whole 12ths. So notice this problem has become 9/12 divided by 4/12. Well, that's like asking how many groups of 4/12 I can get out of 9/12. And that's like asking how many groups of 4 apples can I make out of 9 apples. Notice that the 12 is kind of irrelevant to the operation you're trying to perform here. You really wanted to know how many groups of 4 I can make out of 9. Well, how do I do that? How do I make sense of this? Well, with whole numbers, this is a way to use the whole number knowledge here to see what's going on with fractions. That's really asking how many groups of 4 can I make out of 9. It's that same division that you've been doing all along. Well, how do we do that? Well, we know that I can get 2 groups of 4 would make 8, and there's going to be 1 left over. And when you convert this to a number, remember that we've explained, why we do this is a fourth. The remainder here comes over the divisor, and so we get 2 and 1/4 because that's a fourth of another group of 4 because there's 1 left out of 4, so 2 and a 4th. Notice that when you do this paper and pencil algorithm, that 12 is really not involved at all. And so it's irrelevant. Now, the reason that's important is when kids look at this, they will be tempted to say this was 2 of those third cups and a 12th of another one. Well, what they're really saying, it's 2 third cups and a 12th of a whole cup. And that is actually correct. This is a 12th of the whole cup. The problem is it is not what the problem was asking. It's unhelpful to know that. The problem was asking how many third cups there are. So we always have to relate to the third cup. How much of a third cup is that? It's a 1/4 of another third cup. It is a 12th of a cup, but you see you'd never get 12ths of a cup showing up down here in this paper and pencil algorithm that they're so comfortable with. And we can look at the Cuisenaire-Rod model and notice that it really is, you can see it here too, just noticing that the 3/4, when I look at that subdivision there, that 3/4 really is 9/12. And the third is really 4/12, and you want to know how many of these 4/12 it takes to get up to 9/12. So the Cuisenaire-Rod model also fits this paper and pencil algorithm. And I'll just point out, excuse me, that paper and pencil algorithm is not the one that you learned. This algorithm here is not an invert and multiply, which is what you normally do. But there was no inverting and multiplying happening at the concrete level. There's nothing turned upside down in this area model. It didn't happen in the Cuisenaire-Rod model. So that algorithm that you're familiar with is probably not one that would be naturally developed if you start developing what division of fractions means at a concrete level. Actually, some curricula, when they do teach division of fractions, actually do use a common denominator algorithm. I think this makes sense, and it fits how you develop it at a concrete level, so I would argue that's what ought to be used. So here is what it looks like on the PowerPoint. It looks pretty much like what we did on the paper and pencil over here. And we already talked about this as a common denominator, not an invert and multiply. Okay, let's try a new word problem. So this one we just wanted to do as to show that you can deal with mixed numbers, and also you can move to a situation where you're not dividing by a unit fraction. So in this case, the recipe calls for 1 3/4 cup of sugar. All you find is a 2/3 measurer. You don't want to wash anything. You're just going to do that and try to figure out, how many groups of 2/3 it would take to get you up to 1 3/4. Probably should estimate. We'll probably talk about that at the end. Again, you may not want to deal with the complexity involved in this. This just gets a little bit more involved, especially with the new unit being at 2/3 of a cup. It won't be something that will show up in the wall. Then you have to go find a new rod. So it is a little bit more complex, but we'll just model it just to see. We're going to do the same thing, make a wall, act out situation, and measure it. So we're going to measure how many 2/3 it takes, including what fraction of that last 2/3 it would take if we want to get all the way to exactly 1 3/4. So here's the wall, and notice that's exactly the same wall as we just did, because we need to know what the unit is. We need to know what thirds and fourths look like so we can model this. So let me show you that. That's the same wall we had before. We know what thirds and fourths look like, and we know what the whole looks like. We know how many little units it takes. Again, the wall that's shown in the PowerPoint is the same thing, although they're using 2 blocks, the 10 and the 2, to make up this 12, just because they didn't have a 12 rod when that picture was taken. And we put the ones on the bottom. A little rearrangement there doesn't really matter much. Okay, next thing you do is act out the situation. And this is a little tougher, and may have to make the picture smaller. But we need, let me use this for one, since that's the whole. We need to show what 1 3/4 looks like. So there's 1, and I am going to have to zoom out. 1 3/4. Get all that in there. Just barely going off the edge. So we have 1 3/4. And all we can find is a 2/3 measurer. Well, notice that this is what thirds look like, if you look back to the wall, but we need to measure in 2/3. And so in order to keep it conceptually clear to the student, I think it's good to go find another rod that actually stands for 2/3, so that I keep that unit very, very, very concrete. So rather than measuring in these, because I'll get out to the end and forget what my unit is and start measuring how much of this one it is that's left over, I'm going to measure with these are the brown rods actually, and see how many of the brown rods does it take, because each brown rod is 2/3. So there's the first 2/3 cup I will pour in another 2/3 cup, and some piece of this last 2/3 cup. Well, in order to find out how much of that 2/3 cup it is, I'm going to have to measure it. And if you'll notice, it gets out to about right there. Well, it's running off the end, so you can't really, I'm going to have to make it even smaller. I hope you can see this, that I measured that last one right to there. That's how much I want sugar only up to this point. So how much of the last 2/3? Well, that's 1, 2, 3, 4, 5 out of the 8 it takes to make another one. So that looks like 2 whole 2/3 cups and 5/8 of the last one. So you can see it's a little bit more complex. You can actually see it in the PowerPoint a little bit better. But we're measuring in this whole unit here because we were measuring in 2/3, because 2/3 matches that. Okay, so we got an answer of something looks like 2 5/8 of those 2/3 cups. So if we're going to do an area model, let me move this out of here. So I need to show that we need 1 3/4 cup of sugar. So I can make even some smaller units here. There's a whole cup of sugar. Here's another whole cup of sugar. I want all of that one and 3/4 of the other one, so I'm going to divide all of them into fourths. so they look the same. I do not want any sugar out here. And then it turns out that I can only find I need a 2/3 cup measure is the only one I can find. Well, I need to know what 2/3 looks like. Well, the way to do that is to find out what 1/3 looks like. So 1/3 of a cup is that many. So you do that, that shows that 2/3 of a cup is 1, 2, 3, 4, 5, 6, 7, 8 pieces. So I want the same subdivisions over here. And I'm going to measure 2/3 of a cup. So I'm going to pour the first 2/3 cup in. Well, that's pretty clear. If I pour 2/3 of a cup in, I'm going to fill up this much because there's 2/3 sitting right there in that first hole. And I can go back and put in 1, 1, 1, 1, 1, 1, 1, 1. There's the first 2/3 cup. Let me make that a little bit smaller or bigger. I think I can do it again. Maybe one more time. You can see that still. Let me do it one more, and then I'll just show you what inside it looks like. You know, with my sloppy writing, you can't tell much, but I put ones in each one of those. So there's the first third cup. Well, I should be able to do that again, because if I notice that 2/3 is 8 pieces, when I pour the next one in, I'm going to fill up 8 more pieces. So I'm going to fill up 1, 2, 3, 4, 5, 6, 7, 8. See, I'll go out that far. And I could put a 2 inside each one of those. So there's the second. It's kind of hard to see that too. There's the second 2/3 cup. And then if I just notice, I can't do it all the way again. If I filled up the last third cup, it'd fill up 8 more. 1, 2, 3, 4, 5, 6, 7. It'd fill up the whole thing. I don't want all that. I only want this 1, 2, 3, 4, 5 pieces more. So what is this little piece right here? That is 5/8 of another 2/3 cup. So a little bit more complex, but I've just taken what I started with, broke it into 2/3 cups so I can see what that is, and just start pouring in and measuring and then counting how much are left over at the end. Okay, so then that's what we did. We drew the area model, we subdivided. There's what it looks like on the PowerPoint. It's pretty close to what I had there. You can fill those numbers in, shade them in however you want, as long as you shade in 8 for every 2/3 cup. It doesn't matter where you fill them in at. And what about the paper and pencil algorithm? Well, let's just see that very quickly here. This original problem was 1 3/4 divided by 2/3. And if we just look at what that becomes, well, the 1 3/4 here in the picture turned into units that had 12ths, and so it looks like we've got 12 12ths, and then 13, 14, 15, 16, 17, 18, 19, 20, 21, 21 fourths. So 1 3/4 is really 21 fourths. It's just a new name for 21 fourths, for 1 3/4. That's something that would be a prerequisite for skills, for students, that they've had that skill, that they can figure out an equivalent name for 1 3/4. You can do the improper fraction if you want to change it to 7/4 and then figure out, actually not 21 fourths, is it? That helps me if you think about it. It's actually 21 12ths. Okay? It'd be 7/4. That's the same as 21 12ths. And then you're dividing by 2/3, but notice 2/3 is this 8 12ths. So I want to know how many groups of 8 12ths I can get out of 21 12ths. Well, how do I figure that out? Well, you want to know how many groups of 8 I can get out of 21. And kids are used to doing that. I know I can get 2 groups of 8, and there's 5 left over, and so I'm very comfortable with saying that is 2 5/8. But what are those? Those are 2/3 cups. Okay, so I hope that makes sense, even with the little correction there. Again, the paper and pencil algorithm should come very late. It's not something that happens early. It should only grow out of what you've already done at a very concrete level. And so if you look at what that algorithm looks like here, that looks pretty much like what I had on the paper. Again, this is a common denominator algorithm. There was no inverting and multiplying happening. What we did here fits how it grew out of the materials. And again, the unit is 2/3 cup, so it's not; those are not 12ths at the end, because a 1/3 cup is 8 pieces. So that's why we're doing 5/8. So here's a few notes. We talked before about encouraging estimation. Could have been done immediately when the problem was presented. We modeled that way once to think about, well, what do you think the answer is going to be before we do any modeling here? But now that we've gotten an answer here of 2 5/8, does it kind of make sense that we should expect an answer pretty close to 2 1/2? If you fill 2/3 up all the way twice, that's 4/3 or 1 1/3. And we need to get up to 1 3/4. So we don't want to go all the way up to 3/3. So we're at 1 1/3, and we want to get up to only 3/4. That's not all the way of another 2/3, maybe about halfway. Just using some number sense and getting some estimation there, kids should be fairly comfortable that answer makes sense. Talked about this before. The paper and pencil algorithm should come late. I wouldn't even do it until you've done this modeling multiple times, until it's very internalized and that kids can figure out what really is going on at that concrete and the semi-concrete level. Fits what Piaget has said all along, that you should start at the concrete, go to the semi-concrete, semi-abstract, and when you get to that abstraction ought to be able to be unpacked till you see where it came from. So there's a link between the abstraction and the conceptual understanding. Otherwise, it's an independent, removed from any conceptual understanding, and kids just think they've got to memorize stuff. So it builds on what they already understood. Again, no inverting and multiplying. Eventually, I would never tell the child that, but eventually the child may say, oh, I could have done this if I just inverted and multiplied. And as long as they've already internalized all the other operations, I'd say, oh, that's really nice that you noticed that. Yeah, you can go ahead and use it, as long as you really have the concept about where it came from. Go ahead and take that shortcut if you want to. But if you tell them too early, it short circuits their linking together of that concrete and the abstract. It short circuits making any connection at all between what they're doing with paper and pencil and what is really happening when division is the operation that's happening with the fractions. It messes up their conceptual understanding. So be very, very careful about doing that too soon. And I'd say it's always too soon until the kid figures it out on their own. I don't think I would tell them. That's just my personal opinion. It'd be something to argue about, I guess. So again, even though what we've done here with division is a development with Cuisenaire rods and area models, we believe that that's consistent with what the Common Core is saying. But if you look at the progression document, some people have some alternative ways of trying to make sense of division of fractions. Sometimes they will try to force a modeling that, at least I treat it as forcing a modeling that looks like it's doing an inverting and multiplying. I think you should judge for yourself by looking at that and comparing and contrasting what we've done with what happens in the Common Core. It might even be an assignment that you'll get to do, is to contrast those and maybe even try it with some kids and see what works. Just trying to point out that what we've developed here and what presented to you is not the only way that people look at operations with fractions. Some issues related to that is I would argue that the rods are very precise, And so when the Common Core emphasizes linear models, and then the progressions talk about focusing on number line stuff, that makes sense. But it might make sense to start with the Cuisenaire rods because they are a very concrete linear model, and you might be able to grow from the development at the Cuisenaire rods up into a number line model that makes a little bit more sense. So consider that kind of development, and just knowing that the progressions encourage, and the Common Core makes a big deal about number lines too. So this is just a way to start with kids that are just learning the concept. This is an alternative manipulative that I think makes that a lot more concrete. So that's the end of the division. Again, I'd say go back and review anything that you need to. You can consider whether or not you even want to deal with the division for that second example where you've got some mixed numbers and especially the divisor that's not a unit fraction, because that makes things more complex. I'm pretty sure that the assignment will be that you're going to have to be writing some of your own word problems for each operation, trying to model them with area models and Cuisenaire rods, writing a paper and pencil algorithm, bring that work to class, as many of those as you can model, so that you have an opportunity in class to look at some of those examples and talk about issues, difficulties that you had, or some precision kind of things in terms of expectations about what that model might look like or might need to look like if you were trying to make it the most concrete, the most visually clear, so that beginning students or students who are struggling can really see the relationships. It's, again, not about an adult being able to get the answer. It's about what model does the adult know that might be helpful for a child who's just beginning or a child who's struggling to make those operations, those relationships between the fractions and what the fractions really mean and what the operations really mean, very concrete, so that development is meaningful to the child. Okay, we'll have fun with fractions.